So today we'll be talking about movements in the small world. What we mean is how the molecules, messenger molecules, move in the nanoscale. Actually, by the second half of the chapter, we will not be talking only about the molecules, but we will also be talking about the bacteria, the movement of the bacteria in the nanoscale environments. So our focus will be typically on diffusion, receptors, how the receptors work, and then also how flagellar motors work, which actually pushes the flagellar bacteria. Okay, so we'll first be talking about diffusion. So we'll be looking at it in the, through the microscopic theory. Then we will have a look at the same thing. Now, in the macroscopic scale, we will see how the molecules are captured. The molecules that are moving with diffusion are captured, so that's where we'll be talking about the receptors. And then finally, we'll be talking about self-propelled objects. There we'll be talking about flagellar motors and similar. So, if you look at it in terms of microscopic theory, diffusion itself is actually the random movement and random migration of the messenger molecules in the environment arising from the motion due to what's called the thermal energy in the environment. Okay? So what it actually means is the molecules are typically moving due to thermal energy, and they're colliding with each other. This changes their movement, their directions, and according to all these operations, the messenger molecules hopefully move from one location to the other. And this way we're trying to transmit information using these messenger molecules. So let's first talk about the discussion of the movement of some particle, some very small particle, let's say with the mass of m, and an initial velocity of Vx in the x-axis. For the moment, let's just focus on a single dimension, the x-axis. In that case, we all know from high school that the kinetic energy of such a particle would be mv squared over 2, bless you. So this quantity fluctuates, but it changes. But the expected value of this kinetic energy would be k times T over 2, where K is the Boltzmann's constant and T is the absolute temperature in kelvins. Okay? That's what you already know. So the mean square velocity thus is the expected value of the square of velocity. That's why we call it square. That's why you have the square here. And its expected value, that's why it's mean. So the mean square velocity is now kt over m. You can immediately find it from here. Actually, the 2's cancel and m goes to the denominator. Consequently, now we can talk about the root mean square of this value here, and that would be the square root of this thing. Okay? As an example, let's for example look at this mass m to be a lysozyme protein. And let's try to find the root mean square velocity of this molecule. So the weight of this lysozyme protein is 2.3 times 10 to the minus 20 grams. And let's assume that the temperature is 300 Kelvin for the sake of simplicity. And the Boltzmann constant is a constant. Note that in the Boltzmann constant, pay attention to the units. Here it's in kilograms. So you have to convert these grams to kilograms. And the temperature is in kelvins. Okay? So you can easily plug it in and find the root mean square velocity to be 1.3 times 10 to the 3 centimeters per second, which is slow or fast. What would you say? Do you consider it to be fast or slow? Fast. I mean, if you compare it against electromagnetic waves, definitely it is extremely slow, but actually it's a pretty fast value. Okay? So that would, such a root mean square value would actually be a sizable value. If there were no obstructions, such a molecule would cross a typical classroom in about a second, which is quite fast. In nanoscale, actually, typically, our propagation rates are much, much slower. And this is actually resulting from the fact that, unfortunately, this molecule is not moving in vacuum. There are other molecules in the environment. Although it's moving quite fast, well, it won't be able to move so far because it will be colliding with other molecules in the environment and therefore change its direction. Instead of going, let's say, from this corner to the other corner, suddenly it will turn to another direction. If you consider the one-dimensional case, on the same line, it will sometimes go in the plus direction, sometimes in negative direction. Okay? So that's the major problem. It will be bumping into other molecules in the environment. So the lysozyme protein is now forced to wander around. It's not going in a given direction. It's just wandering around. If you consider the one-dimensional case, it's going forward and backwards. So it will be executing actually what we call a random walk. Okay? Now, if there's no bias in one of the directions, in the plus or minus direction, if there's no bias, would this molecule reach anywhere? No? If there's no bias, that means if there is no bias, if there's no bias, which means the probability of going to the right and to the left is equal. And let's say this molecule starts from the origin. Do you expect it to reach a receiver at some distance d? Is it likely that it will reach there? Yes? No? No? Okay, then let's leave. We have no chance that we will succeed in this.
The stationary probability of is 0 for every directions.
We're talking about one dimension.
Okay. So if we call each point a state,
okay,
like a birth and death process.
He's from industrial engineering, by the way.
So since there is no bias, this is now concurrency, and a possibility to be in a state in stationary is 0 for all of the states. So actually it's not a discrete one but continuous one, so it might reach a destination.
It might reach the destination. Actually, we can put it this way. On the average, if there are many, many such molecules, on the average, some of them will go this way. Some of them will go the other way. If you look at the average, they will be around the origin. The mean will be at the origin. Well, the molecules will be spread around, but the mean will be 0. But that doesn't mean that individual molecules, they're all gathered in 0. They will be everywhere, but if there's no bias, the mean will be 0. But it doesn't mean that they won't reach anywhere. They will actually reach many places. Okay? Otherwise, as I said, we would have no hope, and this topic would be closed. So, for example, if we assume that the molecules are initially deployed this way in a 2D environment, okay? As time passes, they will be spread around, but as you can see, in all directions. If there is some force influencing the molecules in the environment, then that force would be pushing slightly all of these molecules, in this case, in the -y direction. So yes, they're still spread around, but there's more bias towards -y direction. Okay? For example, if there's some inclination, or if there's some flow in the aqueous environment, then the molecules will be spread around, but more towards the -y direction. Okay? But if there is no bias, as in case B, they will be spread in all directions. Okay? Again, this is for 2D. If you consider 3D, they would also be spreading in the third direction. Okay? So, for the sake of simplicity, we continue with the 1D case. So, if you consider the one-dimensional random walk, that means there are many molecules, sorry, but we're focused on, let's say, the ith molecule. So, at time t0, initially, the ith molecule is at position 0, that means at the origin. So each particle steps to the right or the left. Okay? If you're talking about 1D random walk, then we mean in both directions, the probability of moving in any one of these two directions is equal. They're equally likely. And in every step, actually you're taking one step in every tau seconds. Okay? So tau would be your step durations, the time between two steps. And you would be moving at some initial speed of Vx, either in the plus or the minus direction. Remember, we're talking about the 1D case. So the step size itself, the length of the step, is now the speed times the time, which is tau. Okay? So from now on, we'll be talking about this step size, the length of the step, as delta. When we mean delta, we actually mean Vx times tau. Okay, but we'll be mostly using the term delta. So the step size depends on the size of the particle, how large that molecule is, the structure of the aqueous medium, many things like the size of the molecules in the environment, the density, whatever. In general, we will call it the structure of the aqueous medium, and also the temperature. Okay? Because as the temperature increases, the molecules now start moving faster. Okay? So the step size depends on all of these, but we will be mostly averaging these parameters. The probability of going to the right and the left, as we mentioned, since we're talking about 1D random walk, they're equally likely, so 0.5. And successive steps are statistically independent. That means if you took one step to the right, for the next step, your next step does not depend on your previous step. So you could be taking again a right step, or maybe a left step. They're equally likely. Well, you can model a different walk, where their previous step could affect the next step. Or you can make these probabilities not 0.5 but different. Fine, but that wouldn't be called 1D random walk. It would be something else. Okay? We're talking about the standard 1D random walk. And each particle moves independent of all other particles. Okay? That means if I'm going to the right, it doesn't mean that you also need to go to the right, or you'll go to the left to balance me. There's nothing like that. Everyone is making its decision independently. Okay? So this has some consequences. Well, the first consequence is that the particles go nowhere on the average. That's actually what we discussed. So averaged over all particles, the mean will be at 0. So for example, if there's a particle going 3 steps to the right, then probably, I cannot guarantee you that, but on the average over all particles, there will be something that's going 3 to the left. Or maybe one is going 2 to the left, another one is going 1 to the left, whatever. Okay? But they will be, since these are equally likely, they will be balancing each other. But let me emphasize it once again. This doesn't mean that individual molecules do not move. They do move. If you look at the collection of all these molecules, they're balancing each other. And the root mean square displacement is proportional not to the time, but the square root of the time. Okay? Now we will develop more on these consequences. But you can, if you're interested, you can have a simulation of this. This is a pretty simple case. You can have a simulation of this to see that this really works that way, if you're not convinced. So consequence 1 is mean displacement of n particles. Let xi of n be the position of the ith particle after the nth step. Okay? Then xi of n sorry, would be what? The position, the displacement of the ith molecule in the previous step at n minus 1, plus or minus a step of delta. I could be moving to the right, that would be plus delta, or I could be moving to the left. Once again, remember, we're moving on a line. We're talking about one dimension. So wherever I am, the next displacement would be either here, one step to the right, or one step to the left. That's what this one's saying. So what would be the expected value of the position of that molecule, or all molecules, in n steps? That would be the average of the, for all molecules, the average of the displacements. Okay? Molecule 1 would be at x1 of n, molecule 2 would be at x2 of n. Sum these up and divide by n, that will give you the average displacement after n steps. All of them have taken n steps. Note that the lowercase n, the uppercase n, they don't have anything in common. The lowercase n is the number of steps, the uppercase n is the number of particles, number of molecules. Okay, so for all molecules, the position after the nth step. That would be the expected value of the positions of all molecules after n steps. And that would be what? According to this definition, substitute xi of n with this expression. So it would be the average of the displacements after n minus 1 steps, plus or minus some delta, some step size, because some will go to the right, some will go to the left. But on the average, some of them will go to the right, half of them actually will go to the right, the other half will go to the left, so I can discard this. Then I'm left with what? Expected value of the displacement of the molecules after n steps is equal to the expected value after n minus 1 steps. How did I come up with this? How could I write this from here? Okay, mathematically. How did I end up with this from this? Actually, I told it about a minute ago.
You said we discard plus minus deltas.
Okay. But look at the expressions here. This is what?
This is expected value of n.
Expected value of displacement after n steps. Expected value of x of n. Okay? What you see in here. That's the left-hand side. How about this thing? I said I can discard this, the red part. How about this thing? This is what?
Expected value of n minus 1 step.
Expected value of displacements after n minus 1 steps. Should this be n or n minus 1?
There are n particles.
Good. I said uppercase n is the number of molecules. That lowercase n was steps. It is one less steps, but the same number of molecules. We are not discarding the molecules. Okay, so this is all molecules after n steps, and this is all molecules after n minus 1 steps. Okay? So the mean position of the particles does not change from step to step. Pay attention. the position of the particles change from step to step because they take steps. The mean of the whole group does not change. That's the point. Okay? And since the particles all start at the origin, that means after step 0, at step 0, they're at the origin. The mean is at the origin. After n minus steps, n minus 1 steps, they're still at the origin. After n steps, they're still at the origin. Actually, the mean, let me correct it. The mean is at the origin. They're not at the origin. They're in different places. But the mean is always at the origin. Okay? Any questions? Okay. So the expected value of x of n for all n would be 0. Let's look at the second consequence. The root mean square displacement of n particles. Okay? So let xi of n again be the position of the ith particle after the nth step. So same thing, in other words. Xi of n squared would be what? Going back to the definition here. I'm talking about the square of this, so it would be the square of the other. It would be xi of n minus 1 squared plus or minus, because the delta was itself plus or minus, 2 delta xi of n minus 1 plus delta squared. Remember, delta is the step size. Okay? So the expected value of this would be 1 over n of the squares. That's the definition of the expected value. So if you substitute it in here, that would be 1 over n in sigma xi square of n minus 1 plus this thing plus delta square. Okay? On the average, the plus sign is again half of them go to the right, half of them go to the left. Sorry, half of them go to the left. So x square of n would be expected value of x square of n minus 1 plus delta square. And expected value of x square of n would be n times delta square. And this comes from what? Actually, in the first step, x square of n would be delta square. In the next step, you would be adding delta square on that. In the next one, you add delta square. So in every step, you're adding delta square. Actually, that means in every step, these things are just moving randomly around. So the variance increases, but the mean is still the same, as you will remember. So remember, n is the time that has passed up to now, divided by the duration for a step, tau. So expected value of x square of t, sorry, would be, if you substitute t over tau for n, would be t times delta square over tau. And we will be calling delta square over 2 tau, that means half of this, as d, the diffusion coefficient. So what I have in here is twice d, so 2d times t. This is just a definition. That's how we define the diffusion coefficient. In the future, we will be defining things in terms of the diffusion coefficient. This diffusion coefficient is actually, remember earlier I said this step size actually depends on several things like the size of the molecule, the structure of the aqueous environment, and the temperature. All these affect actually D. Now these are separate factors. Each one has a different effect. The diffusion coefficient is actually a merged effect of all these. Okay? So the environment changes. Of course, the environment will change due to one of these factors. I will just look at the impact on D, and I will say, well, the diffusion coefficient of the new environment is this value, and continue with that. Okay? That's why we're defining the diffusion coefficient at the moment. So what you need to remember is the root mean square of x of t would be 2 dt in square root. Okay? Remember that square root of 2 dt, we'll mention it later also. So, again, a simulation exercise for you. This is not homework, it's just exercise, okay, for you. Would be find the distribution of the molecules for different cases. Like the probability of finding the particles at different points x at times 1, 4, and 16 are plotted here. Just try it yourself at different values. By the way, if you try to replicate this, it will be difficult for you because I didn't say anything about D or other stuff. So all parameters are not defined here, but just assume some values. The behavior will be the same. Okay? Just play with D and other parameters. The shape will slightly change, but the behavior will be the same. What this one tells us is actually the following. Starting at the origin. After one step, the probability of seeing that object very close to the origin is very high. The probability of seeing the object further away from the origin is much smaller. Okay? Whereas, if you wait a little bit longer, like 4 steps, now since the object, the molecule, has time to take 4 steps, the probability of that molecule being far from the origin is now higher compared to the previous one. Okay? But note that it's possible that in one trial, the molecule had moves like left, right. Means at the origin. This is possible. This is just a scenario. But if you run it once again, this time it could be left, right. So 3 times to the left, once to the right, that means 2 steps to the left in aggregate. Okay? Try it once again. It could be right, left, right, whatever. Okay? If you run this experiment millions of times and display the ratio or the probability of seeing the object at any specific point, you will end up with this. As the time increases, you can see that it is spreading, which means the probability of seeing this object, this molecule, somewhere here becomes now possible, but not very likely. But it could be anywhere in here. Okay? But now you can see that the probability that the object is waiting at the origin, it ends up at the origin, is now very low. Okay? So you will observe this. So the diffusion coefficient D now characterizes the migration of particles of a given kind. Pay attention, for different molecules, the diffusion coefficient will be different. That's what it says. In a given medium, if the medium changes, things change. At a given temperature, it depends on all these. It depends on the molecules or the structure of the medium. It depends on the temperature of the environment. And also it depends on the molecule itself. Different molecules will behave in a different manner in the same environment. So it also depends on the molecule itself. So consider that D is 10 to the minus 5. Sorry. This object diffuses to a distance of d, let's say 10 to the minus 4, in a time, what? X square over 2d. Okay, where did this one come from? If you look at this side is x square. Okay, x square is equal to 2dt. Okay, so if you take t out of this, the time to go to the distance of x square would be x squared over 2d according to this value of d for this environment and for this type of molecule. Okay, so it would be 5 times 10 to the minus 4 seconds. Remember, we said previously the molecule, if it was in the vacuum, was able to cross a classroom in a very fast manner, in about a second. Now we're saying it can go a distance of 10 to the minus 4 centimeters in this time, okay? So if you decrease the distance to 1 centimeter, increase the distance to 1 centimeter, you realize that suddenly the time increases much faster. Okay? So in order for a particle to wander twice as far, it takes actually 4 times as long. So there's a power of 2 difference. In order for it to wander 10 times as far, then it would be 100 times as long. So the displacement is not proportional to time, but it is proportional to the square root of the time. If you look at 2D and 3D random walk now, let's try to extend what we have done for one dimension to multiple dimensions. Actually, same rules apply. Okay? So in each direction, actually, the movements are independent. That means a molecule might be moving like this. So this is a projection in the x, y, and z dimensions. But the component in the x dimension is independent of the component in the y and also the z dimensions. Okay, so you can consider them to be three independent events. So if expected value of x squared is 2 dt, as we did before, then for y squared it would be 2 dt, and for z squared it would be 2 dt. 3 separate random movements, actually. So in 2 dimensions, if you represent the distance from the origin as radius r, then it would be expected value of r squared would be the expected value of x squared plus y squared. So it would be 4 dt, and for the case of 3 dimensions, it would be expected value of x squared, y squared, and z squared. So it would be 6 dt. So if you start with a single molecule, and let's say we start here at this very point, and now apply here in 2 dimensions a random movement in x and y dimensions, the molecule would just make random movements. As you can see, in some places it's just going round and round around the same place, so it's completely dark. So it's just scratching the paper, and sometimes for some time it's making some movements a little bit away from the previous location, and then again some random movements, and finally it's ending up somewhere around here. Okay? Now this is the sketch of one example run. Run the same simulation once again, it would be something different. Okay? In this example, it's taking 18,050 steps, so n is 18,050. If you look at the curve flight from here to the final point, it's 196 step lengths. That means it took 18,000 steps, but the distance it went was only 196 steps. Okay? Why? Because it's going back and forth, it's just turning around the same points. The expected root mean square displacement would be square root of 2n, so around 190 steps again. Okay? So this is actually how things are moving around, how the molecules are moving around. Okay? So if you look at the general one-dimensional random walk, suppose that a particle steps to the right with some given probability, let's say p, and to the left then with 1 minus p. Then what's the probability that such a particle steps exactly k times to the right if you have n trials, n steps? Out of n steps, k should be to the right. Remember, stepping right would be p. That's how we represent it. Now that would be the binomial distribution. We're trying to have k. Now we define moving to the right as success. So moving to the left would be failure. So we're talking about k successes in n trials. These successes do not need to be consecutive. So it's the binomial distribution. So the probability of having k successes with n trials, where the probability of success is p, was defined, as you will remember from the previous chapter, by this formula. Okay? So your position after n steps would be k delta minus n minus k delta. So it would be 2k minus n times delta. Okay? Do you understand why this is? Are you lost or are you able to follow? I hope you're not lost because there's more to do. Can you find why this is happening? Now, if I ask a question, it does not necessarily mean that it's a difficult question. It's simple. You're taking k steps to the right. So we're talking about your displacement from the origin in the right direction being positive, left direction being negative. You take k right steps. In total, you're taking n steps. So you should be taking n minus k left steps because you don't have the option of remaining at the same position. Every step is either to the right or left. So if you go this much to the right, that means you should have gone this much to the left. So that would be your position with respect to the origin. Okay? So we know the probability of having k successes, hence we know the distribution of x of n. The distribution of the x of n would be the probability distribution of the location of the particle, and note that it depends on the number of steps on n. For example, in the beginning, x0, okay, after 0 steps, your position being k would be what? Initially you're at the origin, so if k is 0, the probability would be 1. Otherwise, it would be 0. Okay? For t equals 0. Now let k, uppercase, represent the random variable which shows the number of steps to the right when you have taken n steps. Out of n steps, how many of them are to the right? That's what the random variable k represents. Now, in the previous slide, we said that that was a binomial distribution. So x of n was, remember this thing, we also talked about that. Expected value of x of n would be what? Look at this, now you're taking the expected value of this. K is your variable, remember. So it is 2 times expected value of k. N is a constant. Delta is a constant. Okay? So that would be the expected value of having k steps to the right. Remember, for the binomial distribution, the expected value is np, whereas n is the number of trials and p is the probability of success. And the variance would be np squared plus np times 1 minus p. Okay? That's already known from binomial distribution. So just try it. using pen and paper. Reevaluate, now assuming that P is 0.5, since you're talking about random walk, 1D random walk, find that expected value of x of n is equal to 0. Remember, we mentioned this earlier, but try to find it out from here. How would you do that?
K is n over 2.
What?
Expected value of K is n over 2. N times 1 over 2.
Yes. Substitute P is equal to 1/2 in here. Expected value of K would be n times 1 over 2. N over 2 in other words, right?
They will cancel each other.
Okay, now if you substitute this value n over 2 in here, 2 times n over 2 would be 1 minus n times delta.
N minus n is 0.
Sorry, this is n, not 1. N minus n would be 0, so 0 times delta, no matter what delta is, 0. Okay, so it proves that. You understand it? Simple. How about this? Now you will need pen and paper. Are you working on it or just looking at me? Is that right? X square of n, if this is x of n, x square of n would be that, right? So the expected value of x square of n would be what? This thing squared, that would be 4k squared minus 4kn plus n squared. Is that right? Multiplied by delta squared. Am I right? And sorry, you should be taking the expected value of this. Since the left-hand side is expected value, you should be taking the expected value of this. And that would be what? Four times expected value of k squared minus 4 times expected value of k times n plus n squared, all this thing multiplied by delta square. This is k. So expected value of k squared is what? This is, or let me write this explicitly. This is what? 4 times this thing, okay? 4 np squared times 4 times this. Let me meanwhile open up this parentheses. 4 np minus 4np plus, 4np squared, sorry. Is that right? That would be only this thing. Minus 4 expected value of k is np. 4np times n, 4n squared p plus n squared. This whole thing multiplied by delta square. Now let me plug in P is equal to 1 over 2. Okay? If P is equal to 1 over 2, P squared would be 1 over 4, so 4s would be cancelled. This is n squared plus, this would be 2n, minus, again 4s would cancel, n, minus 2n squared plus n squared. This whole thing multiplied by delta square. Okay? Now, n square minus 2n square cancel. 2n minus n is n times delta square. And that is exactly what we wanted. Okay? It's easy, it's not difficult. Now let k be a random variable, denoting the number of steps to write in n steps. So it's the same thing. We said k is binomial. If n and np are both very large, then the binomial distribution can be approximated by the normal distribution with mean mu and variance sigma square. And actually, continuous approximation models the physical event better. So we try to find a continuous approximation for this binomial variable, although that's discrete. So if you try to do a Gaussian approximation of k would be, as we said, normal with mu and sigma square, where mu is np, and sigma square is np times 1 minus p. Okay? And this would be the PDF of this normal distribution when you substitute mu and sigma square, you will get something in more detail. If you try to have a Gaussian approximation of x, then x would be 2k minus n times delta. We know time is the time to take a single step times the number of steps, n tau. And we know the diffusion coefficient is delta square over 2 tau. So x would be now a normal distribution with mean 0 and variance 2 dt. Okay? The standard deviation would be square root of 2 dt. That's one of the things you will remember from the first few slides. And remember, 2 dt is actually n sigma square. That's the variance. That's what we found in the previous slide. Okay? But we want to write it in terms of 2 dt when we're talking about diffusion, because we talk about the diffusion coefficient. And this would be the PDF accordingly. Okay? So these are approximations, continuous approximations for k. Remember, when we say k, we mean right steps. Okay? So that's what we define as success. Now let's Now let's look at the macroscopic theory. Up to now what we did was we looked at the individual elements, individual molecules. Now let me look at a group of molecules. What happens with a group of molecules at the larger scale? So consider a position x, again in the one-dimension case, and another position that is delta, or one step to the right. Okay? And let me have a hypothetical surface here and try to find how many molecules are crossing it in a given step or in a given time. Okay, so the question is how many particles will move across the unit area from x towards x plus delta, a unit area of this location in unit time, and what is the net flux in the x direction, and that net flux will be denoted by J of x. Okay, this is not the Jacobian we saw in the previous chapter, so don't worry. So at time t plus delta, t plus tau, that means one step later, half of the particles at x will have moved towards the right, and other half would be moving in the reverse direction. So those moving to the right will have crossed that dashed line here, the surface we mentioned. And half of those that were previously in here would go here, but some other half would go in here. Okay? So if you're looking at the net flux in this direction, that would be number of molecules moving from here to here minus those moving from here to here. Okay? So the net number crossing to the right will be, this is the number of molecules at x, half of them would be going to the right, and half of those at x plus delta would be going to the left as a subtraction. Okay? So that would be the net number of molecules that are crossing. The flux is now this value divided by this A times tau. Can you guess what A times tau represents? A is actually the area that's normal to x-axis. Going back to the slide, this is the x-axis. And this is, if you look at this in 2D, that would be the area. Okay, that's perpendicular to this x-axis. And tau, as you know, is the step size. Duration, not size. The time it takes to take a step. So A times tau would represent what? If you take this area and multiply it with tau, that would actually represent a volume that it would cross. So, the net flux would be the number of molecules over that volume. Okay? One thing, where did this minus come from?
You changed it.
I changed the order. This was x minus x delta. This is x plus delta minus x. The order changed, that's why that minus comes from. Okay? So that's defined as the flux. Okay. So that is the same thing, the flux. Multiply by 1 and do some rearrangement, and you will end up with this. Okay? Now remember from the macroscopic theory discussion that the quantity delta square over 2t is what we define as d. That would be, this thing is d, diffusion coefficient. So the flux would now become minus d times 1 over step size times, this is what? The number of molecules at this place times, actually this is the volume, so let me correct that. Not by time, but by the step length. That would be the volume. So that would define the concentration in that area, in that volume, minus the concentration here. This means what? The flux is concentration at this position, x plus delta, minus the concentration at x times minus d times, or minus d over delta. Okay? So C of x is, as we said, the number of particles per unit volume, in other words, the concentration. So we end up with this. Now, if I take the limit as the step size goes to 0, then this equation becomes partial derivative, and we obtain the Fick's first equation, which is flux is minus d times the derivative, partial derivative of concentration with respect to x. Okay? So what it means is the net flux is proportional to the slope of the concentration function. This means what? You remember diffusion from high school, right? You should. Like you have salty water to the right of the membrane and less salty water to the left of the membrane, and you look at how the molecules move through the membrane, in which direction. Remember that all depended on the concentration. Okay, same thing here. Flux is proportional to the slope of the concentration. If the concentration difference is high, there will be more molecules passing that surface. If the concentration levels are very close, there will be less molecules passing through. Okay? That's what we mean by the slope of the concentration function. Because if the difference is high, the slope would be higher. The constant of proportionality is minus t, as you can see. And if the particles are uniformly distributed, the slope is 0, because concentration at both points would be the same, and therefore there would be no flux, which means there's equilibrium. Pay attention when I say equilibrium. This is an equilibrium at the macro scale. That means if you look at the concentrations would be the same. It doesn't mean there is no flow of molecules. There will be, even in the case of equilibrium. But if 5 of them are going this way, 5 of them will go this way. It doesn't mean the movement has stopped. That won't be the case. That would happen only at absolute 0. So this is explaining that concentration slope. So the flux due to a linear concentration gradient, C2 over C1, C2 minus C1 over some distance B. So there's a net movement of particles from right to left, solely because there are more particles at the right compared at the left, because C2 is higher than C1. If C2 gets lower, closer to C1, this flux will decrease. If they're equal, it will be 0. If C2 becomes lower, then the flux will change the direction. Okay? So that is, sorry, that is actually the first law of Fick's. Okay? Fick's second law is the change of concentration with respect to time, which is minus del flux del x, which is actually, if you substitute it, d times the second partial derivative of c with respect to x. Okay? So if we know the initial distribution of particles in the environment and other boundary conditions, now we can figure out all later distributions by solving partial differential equations. And these are very similar to the heat equations, as you will remember from the last slide of the previous chapter. There, remember, we had, for example, a rod which had different heat values at different points, but at both ends we had these infinite heat absorbers, and we were able to show what the heat distribution will be after some time. Okay? So it's similar stuff. So if you look at Fick's law in 3 dimensions, then it's the same thing written over and over 3 times. Okay? And you can look at you can formulate the partial differentiation of the concentration with respect to time as a 3D Laplacian as d times the second derivatives of c with respect to x, y, and z. If the problem is spherically symmetric in all dimensions, the flux can be then represented as radial. So remember what we had for x, y, and z. And if you write it in 3 dimensions, it would be like this. Instead, if you write it in a radial form, it would be minus d times del c del r. Okay? And therefore, the concentration of c with respect to time would now be d times 1 over r squared del dr by this. Okay? So for example, let's look at diffusion from a micropipette. Okay? So a micropipette filled with an aqueous solution of a green, let's say, fluorescent dye, so that you can test it. You can see how that fluorescent liquid is diffusing in, let's say, a large body of water. At time t equals 0, that is when your experiment is starting, particles of the dye are injected into the water at a rate of I molecules or drops, whatever, per second. The total number of particles injected would be I times delta t in time steps of delta t. And solving the differential equation with these boundary conditions would give you this concentration formula. At a distance of r, in a distance of t, that would be the concentration. So this is a 3-dimensional Gaussian distribution, and the concentration remains highest at the tip of the pipette, but it decreases there as a treehouse of power of the time, as you can see here, t to the power 3 over 2. And an observer at radius r sees a wave of green fluorescent dye coming towards it that peaks at at t equals r squared over 6d at a concentration of c of this value. Okay? So, as homework, derive this and send your homeworks to Gaye. Okay? You can either send it by email to her, to the email address she had in the previous chapter slides. It's gaye.genç@gmail.com, or just leave it to her mailbox. So now let's look at diffusion to some spherical adsorber of radius a. That means r is equal to a. A spherical adsorber means the following. Consider a sphere. The surface of the sphere is able to absorb anything that touches. It has infinite capacity, independent of the number of molecules previously adsorbed. If a new one comes in, it will get that and it won't bounce back. Okay, that's what we call a spherical adsorber. Of course, the aim is to model, for example, what will happen when molecules are sent to a spherical cell, for example. So every particle reaching the surface of the sphere is gobbled up by the sphere. So at a radius of a, the concentration at the surface of the sphere would be 0. It's just taking it and let's say destroying it. Okay, so the concentration of that molecule at the surface will always be 0, no matter how long the experiment takes. And at some faraway distance, the concentration, that means the source, the concentration would be some C0, whatever it is, some initial value. Okay? So the boundary conditions are at C of A, which is the surface. The distance is measured from the center. So at the surface, it's always 0. And at infinity, at the source, it's some constant value C0. Okay? The solution would be that at distance r greater than or equal to A, it would be C0 times r minus A to the r. Okay, so let's continue with the diffusion to capture. So now we're focusing at how the molecules that have diffused in the environment finally reach at the cell membrane and they're taken into the cell. So remember that the steady state rates of uptake of particles by the absorbing objects, the surfaces like the cell membrane, are proportional to the linear dimension of the object rather than to its area. Okay? So it's defined in terms of the radius, typically. So the probability of capture, for the probability of capture, suppose that a particle, a messenger molecule, is released near a spherical adsorber of radius r equal to A. That means consider a cell, a spherical cell with radius A, and a molecule released to that molecule from a distance of d. So the question is, what's the probability that the particle will be adsorbed? This actually means, what's the probability that this molecule with Brownian motion, with random walk, due to diffusion, it will make strange movements, but hopefully arrive or touch the membrane or the surface of this sphere?
Eventually?
Well, good question. Eventually it may, pay attention, I didn't say it will, but eventually it may arrive at the destination cell. But the real question is, you're right, when will this occur? So the probability that this will arrive at the destination at time t is different for different values of t. So given some time duration, it should arrive there. I cannot wait till infinity because this released molecule was representing only one of the bits. That bit has to be decoded by the receiver here in some time so that I can send another bit. I cannot wait for only one bit indefinitely, because in that case my data rate would be 0 bits per second. Okay? So to be able to do that, now I have to define the problem in a way that I can solve mathematically if I'm trying to model it. Okay? Sorry. So let me consider such a scenario. Say this is the origin. Consider a hypothetical sphere. Pay attention, this is hypothetical. There is no surface there. But the molecules are released from this hypothetical sphere. Okay? So at a distance of b from origin. There is an adsorber surface here. Okay? Like the cell membrane. And yet another adsorber surface here. Okay? Then that means the molecules are released from the distance of b. They make random movements. If they touch this surface, they're adsorbed. Actually, they're received by this molecule. If they touch this surface, they also disappear. Now, don't take this. Don't imagine that I'm proposing something like a cell inside a larger cell. That's not the case. Now, this is just a mathematical definition, because in the future, I will extend this radius c to larger and larger and finally infinity. That means it will disappear at the end. So I'm telling you the end of the film at the beginning, but just to make sure that you don't misunderstand this. Okay? So for the moment, rather than giving a physical meaning into this, for the moment, assume, just consider the mathematical problem. I have one adsorbed surface with a radius of A, another one with a radius of C, and from a distance of B, I'm releasing the molecules. Okay? So the boundary conditions are at the radius of A, this adsorbed surface, the concentration would be 0 because it has indefinite appetite for absorbing these messenger molecules. Similar is true for the outer surface at radius C, and at radius B, it's the maximum, C max, or in the figures you see it as C sub m. So from radius B, they're released, and they diffuse towards concentration of 0. Okay? So with these boundary conditions, we can find what C of R is. Okay? So from this radius of B, there's also in and outgoing flux or current of the molecules. So when we try to plot it, the concentration at radius R, remember measuring from the center, the concentration at radius R would be C max over 1 minus A over B times 1 minus A over R if the distance R from that origin is between A and B. That means in this range. Okay? If it's between B and C, that means in here, then it's formulated as in here. Okay? Any questions? This is given, okay, you don't need to derive it. Then the flux at distance R is formulated as in here, as you will remember. So you can find this from here by taking this partial derivative. Just exercise this so that your hand gets used to doing such calculations. But please try to take this partial derivative and you will end up with this. If not, you have a problem. Okay? So we can now talk about the diffusion current. The diffusion current from the shell source, which is the shell with radius B, to the inner adsorber, the one with radius A, is the inward current, which is this value. Now, how did I get this one? If you look in here, if you, for example, focus on this one, multiply the flux with the surface area at distance r. So multiply it with 4 pi r squared. As you will remember, that would be the surface of the sphere. You will end up with the current. Okay? Similar is true for the outward current. So how can we find the probability of capture by the inner adsorber, which is, as I mentioned earlier, our target cell? That would be inward current over all current. That would be the ratio. Because only the ones that are coming towards A would be the ones that would be received. Those that go outward would not be received. So you can find the probability that way. Okay? So you can find it as in here. Just divide them and you will get this. Now if you take C to infinity, taking C to infinity, here means taking this outer adsorbed surface away. There's nothing like that. If you make it infinitely large, that would mean actually you don't have it. Okay? So the molecules would be able to just go out and wander around here. With some very low probability, they may also come back. But probably they will just go out, far away. Okay? So what happens if you take C to infinity? What?
A over B.
It would be A over B. What's A over B? A is the radius of the receiver. B is the distance of the receiver point from the center of the receiver. Okay, so I can write B as R plus D. Remember, it was A, here it is R, over B, which is R plus D. So you can say it's A over B, or you can say it is R over R plus D. What does that mean? What was that, first of all? That was, remember, the probability of the molecule being captured. The probability that the molecule is captured is radius of the receiver over the distance from the center of the receiver, or in other words, distance to the surface and the radius of the receiver. It's straightforward. Want to try this? We did. We learned this the other way around. Before knowing this formula, actually, with the simulations, we discovered this. And it turned out that the diffusion world already knew it. So, okay, let's do some fancy stuff then. Let's try to get the feeling about diffusion, how it works. Sorry. Just 1 second. Okay. Now, this is an animation. Actually, it also contains a simulation behind it. Designed by 2 of our undergraduate students as their CmpE59G graduation project. It's actually part of what they did. The other part was about calcium signaling. So when we come to the topic of calcium signaling, I will also show that. But this is available on my website. So from here you can access it if you want. This address is also given in your slides. So here we are going to have actually a simulation that's being animated. So you can adjust the symbol duration. That means we will be sending consecutive bits, the time given for each bit. When this time expires, this 8 seconds, for example, the default, when that expires, the transmitter will send another bit. The molecules that remain from the previous bit will also be in the environment, and they will also be received. So that will create me a kind of interference, what we call intersymbol interference, because those molecules are from the previous symbol. So this is the interference caused by the previous symbol. The number of molecules here is the number of molecules that are released for each bit. So default is 100. You can just play around with these values. Distance between two cells is by default 6 micrometers. Radius of the cell is 8 micrometers. Temperature is 310 kelvins. The viscosity is given here. Molecule size, environment molecule size. From these you calculate actual diffusion coefficient. The input stream, so we're going to send 10111001. You can change it. You can send anything you wish. And the threshold percentage is, well, you're sending 100 molecules. If 30% of them are received, you assume 1 has been sent. Otherwise, it's a 0. You can play around with all of these so that you can see the effect of symbol duration, the effect of number of molecules that are being sent, effect of threshold, whatever. Let me just run it for the moment with the current values, but later on you can change it. Now we have 1 transmitter and 1 receiver. These are created according to the radius sizes given here. The distance between these two is 6 micrometers. As I said, you can take them apart and see what the result is. You're trying to send the sequence. You will start with the first one. This is showing the scale. Here you have the number of molecules received up to that point for the current symbol. And this black point is where the molecules are being released. Once they touch any part of this surface, that's an adsorber surface, so everything will be, those molecules will be immediately received. As you have seen, we're sending a 1. You see the progress bar going. Molecules, some of them are arriving there, and you see the number of molecules increase there to something like 30. So it went green, saying, okay, I received it. So the first bit has been successfully received. I sent 1, 1 was received. I sent 0, 0 was received. Good. Pay attention. This is not a video running. This is a real simulation going on. So every time you run, you get some different output. We're going lucky. Last night when I tried it to see if it's still working, I got some errors. But seems like at the moment, everything is being transmitted without errors. Errors are possible. Still successful. By the way, pay attention. Now, you have a sequence of 1s that are being sent. That means in every 8 seconds, we're releasing 100 molecules from here. Now it's a 0. Now see, consecutively 100, 100, 100. 300 molecules have been released in 24 seconds. And there are many of them stray out here. That's what I was expecting, and it's happened. Now, since many molecules were released from the previous symbols, they cause an interference, intersymbol interference. Also another one here, 2 consecutive. And these 0 were misunderstood as 1. Now if you increase the threshold here, probably this will not happen. But then it's possible that some of these successful transmissions were misunderstood. Like you could miss once if you increase the threshold. Okay? So play around with this and get a feeling of the effect of these parameters. Try to increase the distance. Try to decrease the cell sizes. Try to increase the number of molecules or percentage that would be the threshold. And see the effect. And this is a report of what has happened. Okay? Just to give you a sense. As I said, this is available. You can play as much as you wish. Okay. If I can find my mouse pointer, we'll continue. Okay. Once again, this is the website. So, let's continue with the movement of self-propelled objects. So, we're talking about flagellar motors. There's a concept of flagellar bacteria that have flagellar motors that allow these bacteria to move. So, we'll be talking about the motors and bacteria, of course, together. So, as opposed to the molecular motors in chapter 2, which were actually inside the cell, and they had very directed transport, because the movement was going on the rails, on the cytoskeleton. So wherever the cytoskeleton goes, that's where the motor goes. So you know how it will work. However, in the case of diffusion, as you have seen, molecules went in any direction. Similar is true actually for flagellar bacteria. They're also less directed. Well, in the case of flagellar bacteria, we're able to little bit direct them. Like you can feed some paths by placing attractants to attract the bacteria that way, or repellents to make it avoid going that direction. So the bacteria will prefer going in another direction. So that's possible. So it's somewhat directed, but it's not like what happens in the case of molecular motors, okay? And the cytoskeleton example. So as an example of this, let's look at the flagellar motor. So we'll be considering Serratia marcescens bacteria, in short S. marcescens. It's a single cell organism and has an elliptic body that is 0.5 micrometer in diameter and 2 micrometer in length. Its motion is caused by the flagellar motors, as we mentioned, and these are flexible helical structures that are 20 nanometers in diameter and 10 micrometers in length. Pay attention, the length of the body is 2 micrometers, the length of the flagellum could be as long as 10 micrometers. This bacteria has from 4 to 10 such flagella, so it's not a single motor, but it has 4 to 10 different motors running. And these flagella rotate at a rate of 100 to 300 hertz. That means 300 times per second. So it's turning quite fast, actually. The propulsion force is approximately 0.45 piconewtons. And in accordance with the Brownian motion, this bacteria is greatly affected by collision with the small particles of its fluid environment rather than its own inertia. But the more important thing is actually this, it starts turning these motors sometimes in clockwise direction, sometimes in counterclockwise direction. It affects, you'll see. It appears that the force of the flagella propels the bacteria in a random direction at approximately 47 micrometers per second for 1 second. That would be the speed, and it runs with the speed for almost a second. Then it stops and changes direction. That's what we're going to see. So note that the flagella can switch the direction of rotation. In the counterclockwise rotation, the flagella bundles into a coil, and this direction is called a run. During that run, the flagella bacteria goes in one way, okay? In a straight line. Then it stops and switches to a clockwise rotation, and the bundle is now uncoiled, and the bacteria goes into what's called a tumble. And during that operation, it changes its direction randomly, okay? So the tumble lasts for only a fraction of a second. So for 1 second, it goes in a line, then stops and changes direction, then it moves in another direction for another second. That's how it moves. The result of alternating these two phases is our own familiar random walk, okay? The direction of swimming or running is changed in response to chemical substances, as I mentioned. For example, some attractants may attract the bacteria in one direction, or you may repel it using repellent chemicals detected in the environment by the cell's chemotaxis system. Just as with the rail walking molecular motors, which we discussed in chapter 2, the cargo now can be attached to the organisms. So the idea, why do I care about the movement of the bacteria? Well, you can actually load cargo on the bacteria. That means load information on the bacteria and send it. Now note that the bacteria is making a random movement, so you better have multiple of those bacteria. And hopefully at least one or few of them will arrive at the destination. Paths of the chemical substances which attract the bacteria, the attractants, can be built to route the cells for data communication, so that it will go in a somewhat directed manner, although not linear. The flagellum is composed of over 20 different protein species, and an additional 30 proteins that are used for regulation and assembly of those structures. The assembly of the bacterial flagellum can be examined in three main parts: the basal body, the hook, and the filament that you see here. The filament is this part. That's a long part. The hook is actually, by the way, if you look at it, this looks like a motor. The hook is holding the filament, attaching the filament to the body, and actually making it rotate with this 90 degrees structure there. And this is the outer membrane of the bacteria, and this is the periplasmic space, then the inner membrane. And here we have the MS ring, C ring, and type 3 secretion systems. You have the L ring here, and there is the rod that is attached to the rings here. So ions moving in and out will actually make this rod turn clockwise or counterclockwise. This will make the hook turn the filament clockwise or counterclockwise. Okay, that's how it works. So the basal body is a motor consisting of a rotor, which is the MS and C rings here, a drive shaft, which is the rod, series of bearings like the L and P rings that are typically used for attaching it to the cell membrane. It has to be attached somewhere so that this filament can turn, otherwise everything would turn together. The stator complexes, Mod A and Mod B in here, and an port apparatus, which is the type 3 secretion system. So the hook serves as a universal joint between the filament and the basal body here. The filament can be viewed as a propeller connected to the motor with its helical shape, and it has a capping protein at the tip, and new subunits are added to the tip for filament growth. The hook and the filament work together to convert the rotary motion going in here, into thrust that will push the body in the reverse direction. And the motion is fueled by the inward directed electrochemical flow of the protons. Therefore, this is called the proton motive force instead of electromotive force. Although there's no consensus on the exact molecular mechanism of the proton motive force in the literature yet, there are some widely accepted theorems. The protons typically flow through the interface between the two types of proteins, which are called Mod A and Mod B proteins, which make up the stator. And each stator contains two Mod A and Mod B proteins. Also, two aspartic acids placed on Mod B proteins exist. And when the proton moves through the channels in the stator, they bind to the aspartic acids in the Mod B protein. And this binding causes a change in Mod A proteins and causes the first power stroke that moves the rotor incrementally. Now, probably you didn't understand much out of this. We will see a video explaining, actually several videos explaining this. So they will make more sense. Let me switch to the videos immediately, and that will give you a sense of what's going on. Sorry. Let me start with this. I'll keep the microphone close, so I hope you can hear it. This is just showing the movement of the bacteria. Oops.
Many species of bacteria propel themselves through their environment by spinning helical motorized flagella. Rotobacter cells have one flagellum each, whereas E. coli cells have multiple flagella that rotate in bundles. Each flagellum consists of a helical filament that is 20 nanometers wide and up to 15 microns long, and spins on the order of 100 times per second. These animations show a series of schematized and speculative models about how bacterial flagella might function and assemble. Just outside of the cell wall, the filament is connected to a flexible rotating hook. The filament, the hook, and a structure called the basal body, located below the cell's surface, make up the three parts of the flagella. The basal body consists of a rod and a series of rings embedded in the inner membrane, the peptidoglycan layer, and the outer membrane. Some of the rings make up the flagellar motor, which can be divided into two major parts: the stator, which is attached to the peptidoglycan layer, and as its name implies, remains stationary, and the rotor, which rotates. The motor derives its power from a proton gradient across the membrane. In this example, a high concentration of protons exists outside, and a low concentration exists inside the cell. The protons flow through the interface between two types of proteins, called mode A and mode B, that make up the stator. Mutational studies suggest that a conserved aspartic acid in mode B functions in proton conductance. Each stator contains two mode B proteins, and therefore also contains two of these important aspartic acids. Although the molecular mechanism of rotation is not known, one possible model describes protons moving through the channels in the stators and binding to the aspartic acid in the mode B proteins. This binding causes a conformational change in mode A proteins, resulting in the first power stroke that moves the rotor incrementally. At the end of the first power stroke, the two protons are released into the cytoplasm. The proton loss causes a second conformational change that drives the second power stroke, once again engaging the rotor. Although the mechanism for motor function is not yet certain, many details of flagellar assembly have been determined. Flagella begin their assembly with structures in the inner membrane. 26 subunits of an integral membrane protein called FLE-F come together in the plasma membrane to form the MS ring. The FLE-G proteins assemble under the MS ring. FLE-G, along with FLE-M and FLE-N proteins, make up the rotor. Flagellar proteins destined to be part of the extracellular portion of the flagellum are exported from the cell by a flagellum-specific export pathway and assembled at the center. Mode A and Mode B form the stationary part of the flagellar motor, the stator. Both are integral membrane proteins, but Mode B is also anchored to the rigid peptidoglycan layer, keeping the stator proteins fixed in place. The subunits of the rod portion of the rotor move up through the hollow cylinder in the assembly, and assisted by cap proteins, build up the rod in a proximal to distal fashion. Another set of rings, called L and P rings, are found in gram-negative bacteria such as E. coli. They penetrate the outer membrane, forming a bearing for the rod. As the rod cap is exposed outside the L ring, it dissociates and is replaced by a hook cap that guides the assembly of the hook proteins. After the hook is assembled, the hook cap dissociates, and a series of junction proteins assemble between the hook and future filaments. Finally, yet another cap is built, and filament proteins assemble. Like the rod and hook proteins, they travel through the hollow channel inside the filament to reach the distal end. The cap rotates, which causes the subunits to build in a helical fashion. A complete filament can consist of 20,000 to 30,000 subunits.
Another one, this is quite short, only 6 seconds, showing the movement of, again, the Have a look at these bacteria. As you can see, there's first the run and then the tumble. And yet another short movie. Which is, sorry, it's difficult to shoot it. Here you see the obstacles where the bacteria cannot enter. So you see the bacteria moving in here. It goes this way, so I will stop here. I won't repeat it. I'm sorry. This shouldn't have started. Okay. Oops. So you can find the pointers in here, bless you. So we have a few slides, so let's finish that stuff. So there is yet another kind of motors, that's the synthetic DNA motors. So it's possible that not only to compute with DNA. Remember we discussed about computing with DNA and having the finite state machine implementation with DNA that has been done. But it's also possible to construct synthetic molecular motors directly from DNA by creating the proper three-dimensional connections between the DNA strands. So a molecular switch component for a motor can be constructed such that it changes the shape based upon external conditions, such as temperature or the ionic concentration. So by generating the correct nucleotide sequences, you can confidently control what components will connect together or hybridize. So the DNA has a persistence length of 50 nanometers. So for devices that are built from shorter sequences of several nanometers, the components are considered to be stiff and straight. So a single-stranded DNA has a much lower persistence length and is very flexible and can act as joints. Making use of the restriction enzymes, you can cut the DNA at specific points as you wish, and the spiral shape of the double strand can be flipped from a right-handed helix to a left-handed helix. That's important, so you can change the rotation order. Or a strand with a longer, better match can replace an existing strand, so you can switch those strands, which will cause a change conformation. And that actually brings us the motion. So the strand exchange technique has been used to implement a wide variety of different mechanical devices, such as the nanoscale tweezers to pick up atoms or small things. And the autonomous DNA devices have been created that traverse along double-stranded RNA and carry a payload for information transportation. Yet another option could be the use of the catalytic motors. So a catalyst, as you know from chemistry, is a substance that either increases or decreases the rate of a chemical reaction. And the catalyst generally reacts with the input chemicals, forming some intermediate substances. Then these go into, again, a reaction. And this final reaction gives us the product which we want. In addition, it regenerates the catalyst so that it can continue this process. One of the most well-known examples of catalysis is the increase in the rate of decomposition of hydrogen peroxide into water and oxygen. If the catalyst is distributed non-uniformly, and an unbalanced force or net torque can be generated. Okay? So if the catalyst is attached to one side of a cellular scale object, for example, it may increase the rate of motion, for example, on that side, so that the object will move. You can also direct it by increasing the rate of reaction on one side and decreasing the rate of reaction on another side. You can rotate, change the direction of the cellular object also.